Hello everyone, the topic of this video is Riemann's rearrangement theorem. But before I introduce this theorem, I need to talk about some knowledge we should know first. All series in real number can be separated to three cases. Now we three cases. The first case is diverge. The second case is absolute convergence, and third case is conditional convergence. Diverge means that the sigma n from 1 to the infinity an tend to positive or negative infinity, or the value is not exist. And absolute convergence is that if we take absolute value of every term of the series will also converge. But if the series is conditional convergence, the series will become divergent. Now we talk about Dirichlet's rearrangement theorem. For any sequence in real number, if the sequence converge absolutely, then no matter we doing what rearrangement on the series, the value of the series will not change. But how about doing rearrangement on series which is conditional convergence? Before I answer the question, we can first prove that if we take absolute value on sigma n from 1 to the infinity an, and the series is converged, then sigma an is also convergent. We prove it by separate the series on to positive term and negative term. And the positive term, and we define that Pn equals to maximum of an and 0. Qn equals to maximum minus an and 0 for every n belongs to positive integer. Then we have the absolute value of an equals to Pn plus Qn, and an equals to Pn minus Qn. Since the absolute value of the sequence is converged, by the comparison test, we can get sigma Pn and sigma Qn both converge. And based on this, and an equals to Pn minus Qn, because sigma Pn and sigma Qn both converge, so sigma n is also converged by the algebra theorem, and we prove the theorem. And now we can talk about Riemann's rearrangement theorem. For all real number L, exists a rearrangement such that sigma n from 1 to the infinity ank equals to L, or positive and negative infinity. We can talk about an example of the theorem. Consider a series n equals 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 and 1 over 5. This series is converged by the alternating series test. But if we take absolute values on every term of the series will become diverged because it is P series and n equals 1. So sigma an converges conditionally. And we can get the value of the series by the power series method. Consider 1 over 1 plus x. Consider a power series of 1 over 1 plus x, and we integral it both sides. We get natural log 1 plus x equals to sigma n from 0 to infinity 1 over 1 plus n multiply negative 1 to the n multiply x to the 1 plus n, and we plug in x equals to 1. We get the the series 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5 equals to natural log 2. And now we rearrange it. One positive term match two negative term, such that 1 minus 1 over 2 minus 1 over 4 plus 1 over 3 minus 1 over 6 minus 1 over 8, and we get 1 over 2 minus 1 over 4 plus 1 over 6 minus 1 over 8. And finally, we get the value of the series is 1 over 2 natural log 2, which is different to natural log 2. And the second arrangement is two positive term match one negative term, such that 1 plus 1 over 3 minus 1 over 2 plus 1 over 5 plus 1 over 7 negative minus 1 over 4. And via some effective mathematical value, we can get the answer of the arrangement is 3 over 2 natural log 2. Actually, the corresponding value of the rearrangement is natural log 2 plus 1 over 2 natural log the number of positive term over the number of negative term. Can we find an arrangement such that the value is exactly 1? The answer is yes. And now I have a simple proof for Riemann's rearrangement theorem. If sigma an converge conditionally, we can say that limit n tend to infinity an equals to 0. And the same to the previous proof. We also let Pn equals maximum of an and 0, and Qn equals maximum minus an and 0 for every n belong to positive integer. And by the squeeze theorem, we can get limit n tend to infinity Pn equals to 0 equals to limit n tend to infinity Qn. And we also have the absolute value of an equals to Pn plus Qn, and an equals to Pn minus Qn. But since sigma n from 1 to the infinity an is infinity, tend to infinity, so at least one of sigma Pn and sigma Qn is infinity. But we also have an equals to Pn minus Qn, so Pn and Qn must be both tend to infinity. Now we let n positive equals to n positive is all positive term of the series, and n negative is all negative term of the series. And we list their elements from little to large as follow. Then we have PLI equals to ALI, QLI equals to 0, and PNJ equals to 0, QNJ equals to ANJ for every I and j belong to positive integer. And hence we have limit I tend to infinity ALI equals 0 equals to limit j tend to infinity a and j, and sigma n from 1 to the infinity ALI equals to tend to infinity, and sigma a and j tend to negative infinity. Suppose given an arbitrary real number L larger than 0, and we keep adding ALI to 0 until passing to the right hand side of L, such the picture. And if we once we passing to the right hand side of L, we start to add A and J to the value to the current values until it passing through the left hand side of L. And we doing it continuously, but we know we know that the limit of a, li, and even j are 0. So that value will finally tend to L. And so the secret is equals to L, and we prove the theorem. The video is ending. Thank you for listening.